Hello B-Sides, happy for having me. This is my first time on stage, and so please bear with me. Welcome to my talk, and we're going to demystify DPAPI. My name is Daniel. I'm a red teamer and former penetration tester. Most of the time penetration testing, since 1 year red teaming. I'm working with Code White, and as an offensive security person, I like credentials, and I want to show you one of my favorite ways to actually get some. So, who wants to learn about DPAPI? Great. What is DPAPI? On a Microsoft Windows system, you encounter this many, many times. With that, credentials are stored, which are, on the other hand, very valuable for attackers, as the access is hard to distinct from legitimate usage. It is quite valuable and crucial for penetration testers and red teamers alike to retrieve that. Where do we have DPAPI secrets? The usage is all over the system. So you have credentials that are saved from within the task scheduler. You have credentials in the credential manager holding logon credentials for your Active Directory domain. The credentials necessary for your AAD Connect secrets are stored that way. And a whole bunch of third-party tools use DPAPI for their secret protection. You maybe encountered a secret encryption in, for example, a .NET Web Config file. And of course, the credential manager and browsers encrypt web credentials with DPAPI. For example, Google Chrome has some sort of DPAPI encryption, and in the past, Microsoft Edge and the Internet Explorer always relied on DPAPI encryption. So let's go into the internals. The data protection application programming interface, really long and boring, consists of actually only 2 methods, which is great. There are a C and a C# or PowerShell version, which is crypt protect data, which maps to protect in, for example, PowerShell, and the crypt unprotect data maps to unprotect. That's quite easy, right? The idea of DPAPI is basically encryption at rest. So when Microsoft designed the data protection API, the idea was that if an attacker managed to fetch these encrypted credentials from, for example, a backup, they should be safe against attackers retrieving these credentials in plain text. And they did, well, quite a good job developing a system which works, but that has some caveats. The hardest part of a crypto system is key management, and for Microsoft, they have automatically built it in. So a user will normally not be involved in DPAPI encryption and the internals of it, so Microsoft manages automatically. We can see here the important files and directories. We differentiate for these listings between the system user, which is above the administrator user, which has a somewhat special role in DPAPI. We can see here the master key directories. We have 2 of them, which are only differentiated by a subfolder called user. And we will get to that specific folder or to the differentiation eventually later on. The system credential files are found in the system profile app data directory, partly in local, partly in roaming. But they are stored there. For example, if you configure a separate set of user credentials that should run a task at 12 a.m. as an administrator, the credentials will be stored under this location. Here we can see a directory listing for the master key directory. We have the system security identifier name as a directory, and we have, for example, the preferred file, which holds the current active master key. The preferred file is 24 bytes large, so it only holds the actual factual name of the currently active master key GUID. For the user, we have the master keys stored, which is quite interesting for attackers when they only have access to the user context. In their app data roaming profile, which is quite common for an Active Directory setup, because as a user, I want to have my secrets on that PC and the next morning on the other PC, and that is where these credentials will be transferred to. The credential files are stored also here in the app data local and roaming directory. So it's quite typical to the system profile, but it's just in the app data user directory. We can see here a directory listing of the master key directory, which is slightly different. We have here, for example, the credhist file that stores old user passwords, but encrypted. For example, when a password change is initiated by Active Directory or by the user, there will be an encrypted version of the old password, and when the password change will be conducted, actually the syncist will be checked if master keys need to be re-encrypted with the user's password, so the new password, and if the password hashes that are stored in the syncist file are not changed, re-encryption of the master key will happen. Maybe I have left that out. The master key of system and user, so every master key, is basically encrypted with the user's password. So in order to retrieve the master key from the encrypted master key file, an attacker or a user need to know essentially the password. What we also see here is a file prefixed with a BK dash. That is the public key of the backup master key used to additionally encrypt each user's master key. That sounds quite complex. And I won't go into details here because we focus on the user's client machine, but I can assure you the domain backup master key is also a fun topic to dive in. So we can see here the directory that holds the user credentials. You may have noticed in all these directory listings that I need to append the /a to the dir command because these are sometimes system files, sometimes protected files, and you won't see them otherwise. So this is the most easy way to list those files. The user credential files are also just global unique identifiers, but missing dashes. And as a rule of thumb, master keys have dashes and are lowercased. Credential files have no dashes and are all uppercased. That's relatively simple. So what can we do with this now? We assume that we want to extract the files for offline usage for now. And if the password is known, we can decrypt the master key, use the master key and the user's security identifier, which is crucial, to decrypt a credential file, and then we can enjoy the plaintext credentials. So most of the time, if you're an attacker and you have access to a user context, for example, you have successfully phished a target, or you have, for example, gathered the NT hash or the cleartext password from somewhere and are accessing a system where the user has stored credentials in the app data directory, for example, you can pull them off, for example, via SMB, and can decrypt these files locally. The beauty of it is you only conduct file access signals. So it is quite low noise for defenders to actually notice that someone retrieved the credential files or the master key. Let's assume we don't have the password, but we badly want it. What we can do is we can use the master key for offline password brute force, which is quite good. This works most of the time quite well, as we can see here. But there is one caveat. It is slow. Like 11 times slower than cracking a DCC2 hash. But the context to get this opportunity is within the current user, so you don't have to dump the LSAS process, or you don't have to dump the SAM or whatnot to retrieve these domain cache credentials. As a user in the user context, you can just fetch the master keys to you. So, bad passwords and password policies help in this case. And as red teamers, we humbly accept password policies that match season changes. We can see here a credential hex dump. Why would I want to show you such a hex dump? It's quite easy, because sometimes you are in an assessment or in an engagement and you are like, okay, what is this file even doing? What is this file even about? And if you have a look at such a file, you can see here in yellow the version information. The first one is from the credential file itself. The second one is from the master key, from the credential GeoID, and the third one is from the master key GeoID. We can see in blue the size of the credential file, and the most important one is the green one, which is the master key GeoID that matches the credential file. So in order to decrypt the credential file, you have to find the matching master key, which is important, as it only opens up to the right key. Another note, this is little endian. Most of the things on a Windows system are little endian, not all, but most. So the credential file is also little endian. And you can notice the 3A, 4A, CAF33 in the hex dump. And when we go and use, for example, the the example script from the Impacket project, there is the DPAPI script that gives us a summary of information, even if we don't have the password or the master key for the credential file. We can see here in green the GUID master key, and that is the one we need to retrieve. So I've now talked about the internals of DPAPI, and you may now wonder what these secrets even look like. There are common ways to store DPAPI secrets, and the most common ones are they're stored in registry as a binary array, a plain serialized PowerShell secure string in a file, or a PowerShell PS credential structure serialized in an XML file, a manually encrypted blob, or all of the above with multiple layers of base64 for good measure. It happens. So here I found an encrypted string in a registry in my lab environment. The parent registry key holds the value civilization6.exe. Nice. The example also shows how to decrypt from registry with PowerShell. So you don't need the current user's password because you're in the current user's context and can utilize the currently loaded master key for that user to decrypt DPAPI blobs. The next example is PowerShell's secure string, and this is one thing that you may encounter quite some time because there is a popular tutorial out there recommending this way of storing credentials for PowerShell automation. And if you retrieved such a file in your engagement and can't decrypt it, there is one thing you need to know. You have just fetched an UTF-16 file from the Windows system. You need to convert it to UTF-8, strip the first 3 bytes, strip the last 2 bytes, treat the written content as real hex values. Then it should work. That's one thing that will maybe cost you 10 to 60 minutes. But the other thing is you can just copy and paste the text and treat it as a hex value. This is a PS credential structure serialized with CLI XML. We can just decrypt the password value by treating the text as hex content as formally with the secure string, but it is also recommended sometimes to export this PS credential structure to more conveniently handle credential storage, encryption, and usage. As a side note, this only works in the current user's context, of course. I want to give you an impression on how DPAPI content can be programmatically created. So I have 2 functions for you. The first one is get protect, and the other one, unsurprisingly, is get unprotect. For both functions, we use an enum field of current user. We can see it there and there. And we pass our secret via $secret and $secret bytes to protect and unprotect. And we leave the second argument empty. We will cover that later. And this is an example of encryption and decryption using DPAPI, and should serve as an orientation for when you start looking at a hex dump of a file. And you're like, okay, what are you now? Maybe you get an idea now what you're looking at. Next on, what is DPAPI entropy, you may ask? Well, let's see. In the former example, we had the $null value supplied to the protect function. and that is actually the entropy value. This is thought of by Microsoft as an application-specific key. Without it, other applications can decrypt secrets created by the user or other apps. So it is some sort of secret, but you get the idea. They thought of encryption at rest, but then there was this problem of how do we handle this in the same context of the user when another application that might be malicious wants to decrypt secrets from another, let's say, storage or location or registry. So they came up with the entropy, and every application need to come up with some sort of entropy. For example, the popular automation software Chocolatey comes with the entropy key Chocolatey. So it's not that hard to get the information what the entropy is as an attacker, but it is some light barrier. And it is, of course, crucial for the decryption process. What is the data protection scope? That is another fun one, and actually my favorite. Let's see. In our PowerShell example, we also set a data protection scope. So that one was current user. C# or PowerShell knows only two values. The first one is current user, which is 0. That results in encryption with the current user's master key. So fine. The other one is local machine, which is 1. That results in encryption with a machine-wide master key. So, okay, what is this local machine about? According to Microsoft's documentation, the local machine enumeration value allows multiple accounts to unprotect data. Use this value only when you trust every account on a computer. For most situations, you should use the current user value. Okay. So we have user, we have system, we have local machine. Let's see what that means. Our first gotcha, secrets protected with local machine context can be unprotected by all users of the system. Recall that master key directory for system. There was a user directory. Master keys in there are used for the current user context. So user means current user context. And master keys one level above are used for the local machine context. It may happen that developers are confused on how or when to use the local machine context, and they might be mistakenly choose it for protecting information that should be only be accessible by system. For example, imagine an application that performs administrative tasks on a system, has, for example, also service privileges, but need that specific named account. And if the developers mistakenly select for the DPAPI context the local machine because, well, the credentials are for the local machine, that is a mistake, then every user on the system can use these machine-wide master keys to unprotect the credentials if they have access to the destination. The second gotcha is the unprotect function itself. So Hamberwolf has found a critical vulnerability by exploiting this behavior. And that is a really interesting one, for me at least. They send an auth cookie to the web app that gets DPAPI decrypted with the current user context. And their plan was extract a master key from the appliance of that web application, mostly the oldest one, encrypt the cookie with an administrative value they know using the extracted master key, choose the local machine context for protect, send the cookie, and on the other side, the local machine DPAPI encrypted secret gets decrypted and they have admin access. And the reason why is DPAPI unprotect has no concept of local machine or current user. Unprotect uses the underlying C API, the crypt unprotect data, and according to the documentation, there are no flags that reflect that specific option. So unprotect will always look into the encrypted DPAPI data stream, and there the flag is set for current user or local machine. Thank you everyone for listening. If you have any questions, please let me know.
Who would like to start with the questions? Raise your hand, please. Then I will start with one.
Sorry, I did not fully get the last privilege escalation. Why did we get the admin access?
They managed to fetch an old master key from the local machine context of that image of the web application, which is normally used in Hyper-V or another virtualization platform and plugged in as an appliance. And they managed to use that quite old master key or the oldest one they could find to have the most targets affected, and used that master key to encrypt or to protect with the local machine scope a value they know is administrative. And the web application has no other choice when that cookie goes through the unprotect function to unprotect the cookie with all the local machine keys the appliance know, and they're logged in, which is quite novel, I think.
Next question, please. Then I will come with a question. As a blue teamer, how could I detect a abuse of a DPAPI by an attacker?
That is quite challenging because in the offline context, you can only know that some remote source tries to read that file, for example, the master key, and in a short period of time, maybe a credential file. Looking at file access to the master key from maybe a source like a service process might be something to be onto, or something odd like why would Notepad access a master key file? But that is very attacker tooling specific, so it is quite hard to have an eye on the master keys of a user.
Last question by someone? And I would still have another question. It's so nice to talk to you. How about hygiene? How can you do something good in your company to do good hygiene for the not abuse of DPAPI?
This applies to basically every crypto system that tries to protect credentials at rest. For example, also password managers. Users and administrators alike do not need to have a password.txt file next to the credentials that are encrypted. So a DPAPI or every other encrypted password manager may be rendered useless when plaintext credentials are stored accessible to an attacker. So this should utterly be avoided.
Thank you very much. So everybody, let's again give a big applause to our Daniel Küppers.